Hi, everyone. Thanks for joining us today. I'm just gonna jump right in. My name is Caitlin, the marketing coordinator here at TestEquipmentDepot.com. We're located in Massachusetts, a local-based distributor for all the best of test and measurement equipment, and we have been in business for more than 30 years. I'm here today with solar field expert, field application specialist, Will White from the Fluke Corporation. How are you doing today, Will?
Doing well, thank you. How's it going with you?
I'm really excited to bring this presentation to us all today for the Solar Tools division of Fluke. Tools and techniques for commissioning and maintaining PV systems. If you do have any questions during the session, please drop them into the chat. We'll revisit them, poke Will's brain a bit, get some more information out there. And as always, if there's any equipment or tools that you're interested in, specifically the Fluke solar tools, we have them in stock. We have the salespeople ready to go. If you need a quote, we can get you that. I can put you in contact with them so that you can make sure that you make the right purchase for you. That's going to do it for me. Well, the floor is yours.
Great, thanks, Caitlin. My name is Will White. I'm the solar application specialist here at Fluke. Been in the solar industry since 2005. I've been NAVCEP certified PV installation professional since 2006. I spent 10 years working for an EPC, mostly doing residential small commercial projects, mostly in operations management. Ended that job as a director of operations for the East Coast. And then I worked for Solar Energy International for 6 years. I spent 5 years building curriculum and updating course content and teaching, and a year as director of business development. And I joined Fluke at the end of 2002, so it's been about a year and a half. So in this course, we're going to talk about the tools and techniques we use when we're testing solar installations, from installation all the way through operations and maintenance. First, we're going to start talking about CAT ratings, how they apply to the testing that we do in solar, and how to select the correct tools to meet the appropriate ratings for the tests that we need to conduct. We're going to talk about IEC 62446-1, which is a standard for testing grid-connected photovoltaic systems. That's a standard that's a requirement in many European countries and is a good guideline for testing our systems here in the United States. And finally, the bulk of the presentation will be going through the solar workflow, looking at all the tests that are done when we're working on solar, from installation through commissioning and then into operations and maintenance. So the first thing we need to know is what's a transient voltage spike? Transient voltage is a momentary unwanted spike of voltage. They can be very quick, they can be very high. Usually they're coming from the utility. It could be caused by many different things. It could be from motors in a building if you're in a commercial setting. Could be from an equipment malfunction, load switching from the utility. Lightning strikes are a big one in the DC side. They're mostly invisible. You can't see them with a regular multimeter. You can see them with the higher end power quality meters. They're very short, very fast, but they can be dangerous. And the important thing to take away from this slide is this last bullet, that if you have test equipment and you're doing voltage testing and you get a transient voltage spike, that could overwhelm the meter. It could damage the meter. It could cause a safety hazard to the technician. So you need to make sure that you have a test equipment that is able to withstand these transient voltage spikes. So how do we know if it's going to be able to withstand that? The first thing we need to know is the category or CAT rating. There's categories 1 through 4. I'm going to start with the most hazardous one, which is a category 4. That's the closest that we're going to be testing to the utility. That's our point of interconnection, our meters, our main service disconnect, medium voltage transformers. From there, we move to category 3. That would be things like our main load center. Solar arrays are considered a category 3 environment by the IEC standard. Then category 2 is our branch circuit wiring. That's things like our outlet circuits, lighting circuits, things like that. There is actually a category 1, that's things that are not connected to an electrical system. So a solar street light would be an example of that. So we know that a solar array is a category 3 environment. We need to have tools that are rated for that category rating. It's also important to know the voltage. We're going to talk more about that in the next slide. But if we have a category 3 rated tool, as an example, a 1500 volt category 3 rated tool is going to have better protection than a 1000 volt rated category 3 tool. So we need to have a tool with at least category 3 rating, or category 3 rating. Once we know what environment we're working in, we need to know what voltage we're going to be working on. In solar, we measure everything from 30-40 volts of a single solar module up to 1500 volt DC systems. AC side could be anywhere from 120, 240, 208, 480, even up to 600 or 800 volts on the output of utility scale inverters. When we look at our tools, we want to make sure that we have the appropriate category rating. So category 3 for solar arrays, category 4 if we're working at the point of interconnection, and we need a voltage rating higher than the voltage that we are testing. And so we need both those category and voltage ratings. Another important thing is the last bullet on the slide. Currently, we need to make sure that our meter leads are also rated at the same or greater rating than what our meter is rated for. So we have a meter, the 393. It's a category 3 1500 volt rated meter. It comes with category 3 1500 volt rated test probes. But if they were to be damaged, you might want to take a test lead off of a different meter, and maybe those test leads don't have that same rating. So they might be category 3 1000 volts, which are much more common. If you're testing on under 1000 volt system, that's fine. But if you're testing a 1500 volt system, those test leads would not be appropriate for use in that meter. As I mentioned in the last slide, that voltage rating and the category rating makes a difference in the safety. So in this example, a category 3000 volt rated meter is designed to withstand 8000 volt transient voltage spikes, where a category 2000 volt meter can only withstand 6000 volts. So they're both rated to 1000 volts, but they have different category ratings, so different safety factors there. Another interesting point, and this I've found with meters that are coming from being imported specifically from China, although some European models as well, they may claim to be able to test up to a certain voltage, but when you look at the category and voltage that they're actually rated to, they're lower than that test voltage. So they may say that the meter can test up to 1500 volts or even 2000 volts, but when you look at the category rating, it might be only category 3000 volts. So that's something to look out for, because they don't have the safety factor built in that a tool that was appropriately rated would have. So how do I know what my meter is rated for? If it's a new meter, it's going to be marked right on the meter. All Fluke meters have them printed right on the front of the meter. This is a multimeter rated for category 3 1000 volts and category 4 600 volts. It's very common to have a higher rating, voltage rating at a lower category. And so this category 3000, category 4 600 volts is very common. The 393 clamp meter is 1500 volts, category 3, 600 volts, category 4. We have a new multimeter coming out in a couple of months, the 283 multimeter, which is category 3, 1500 volt, category 4, 1000 volt rated. So that's good for those 800 volt systems. So clamp meters, same thing, category rating and voltage right on them. Here we have a series of 3 different meters, the 325 clamp meter on the left, the 378 clamp meter in the middle, and the 393 clamp meter on the right. It's all category 3 tools, but they go from 600 to 1000 to 1500 volts. And the scale of these pictures are relatively similar to their physical size. As the category and voltage rating goes up, the physical size of the meter gets bigger. And that's add additional safety factors at that higher voltage level. And when we're buying test tools, it's important to know that there's a big difference between something that's listed to a certain standard versus something that's designed to a specific standard. There are several standard organizations, IEC, UL, they create standards. There are other organizations, nationally recognized testing laboratories that test to certain standards. Some manufacturers will design their tool to a certain standard, but they don't actually have it third-party verified. Fluke Tools, we actually send our equipment out to a third party who tests to the specific standard to make sure that not only is the tool designed to that standard, but when you test it, it actually meets the requirements of that standard. So all of our tools, third-party tested, so you know that they're going to meet those standards for the category and voltage ratings. Okay, moving on to the IEC standard. IEC 62446-1 is the standard for testing grid-connected photovoltaic systems. It is used predominantly in Europe. It's a requirement to test to this standard when you're installing or maintaining the system in Europe. Here in the US, it's not required, but it's a really good standard to use as a guideline. In this standard, there are two categories of tests. There are safety tests and performance tests. For the safety tests, they require testing of the continuity of the equipment grounding conductor, so making sure our metal parts are actually bonded together. We're testing polarity, voltage, and current of all of our PV circuits. We're going to test to make sure all of our components are functioning properly, the disconnects work, breakers are working properly, the inverter is working properly. And we're going to do insulation resistance testing of the DC conductors to make sure that the insulation hasn't been compromised. Now, performance testing includes IV curve tracing and thermal imaging as well to make sure the system is actually operating the way it should be. Now, in this presentation, we're going to look at the installation, commissioning, and operations and maintenance sections of the product life cycle, the system life cycle, because that's where the testing is done. And as a test equipment manufacturer, that's what we're mostly concerned with. So during installation, there's a couple tests that we're going to do. The main one is insulation resistance testing. This is going to be used to make sure that the insulation hasn't been compromised during installation. We're also going to use it to identify locations of ground faults. Essentially, what an insulation resistance tester is doing is it's sending a high voltage, low current through the conductor. It's essentially charging that conductor up and then looking for current leaking to ground. The important things to know when you're doing this is that that wire can't be connected to any other circuits or any electronic equipment because the test won't function properly. So it's really a good idea to do insulation resistance testing at installation after the wire is installed in the conduit, but before it's terminated on any terminals like at an inverter or a combiner box. We have a series of insulation resistance testers at Fluke. The 1587 and 1507 are small handheld insulation resistance testers like the one seen in this picture. They can do up to 1,000 volts. The SMFT 1000 is a solar multifunction tool. It can also do insulation resistance testing up to 1,000 volts. And not listed on this slide is the new 1537, which can test up to 2,500 volts in 100-volt increments, which is a really great insulation resistance tester for utility scale projects that are working at 1,500 volts. Now, during commissioning, after everything has been installed, but before we've started to energize things, we're going to do voltage and polarity testing. Voltage is to determine that we have the right number of modules connected in series. So if we have too high voltage, that means someone connected too many modules in the string. If the voltage is too low, we have too few modules in the string. And usually those two problems are paired together because someone put too many modules in one string and not enough in another. We're going to test polarity before we commission the system, before we close any fuse holders, to ensure that the positives are all connected to positive and the negatives connected to negative. If things are wired backwards, we can have current flowing through the circuit, which can cause problems when we go to open up fuse holders. They can arc and cause damage to the fuse holder. They could be a safety hazard, obviously, to the technician. Now, any multimeter or clamp meter that can do voltage and polarity testing can do this test. We have a whole series of both multimeters and clamp meters for these purposes, from 600 volts all the way up to 1500 volts. The 393 clamp meter, which is shown in this picture here, is rated for category 3, 1500 volts. We do have some Amprobe models that are rated to 1500 volts, category 3. We have a new meter coming out, the 283, which I mentioned before, which will also be able to test up to 1500 volts. And the SMFT 1000 can do voltage and polarity testing as well. Another test that's done during commissioning is IV curve testing. And this is checking to make sure that our modules or strings of modules are performing the way they should be. We typically see utility scale projects being IV curve tested at commissioning, and they'll oftentimes test the entire system. We don't usually see IV curve testing in residential or even small commercial systems at the time of commissioning. It's more used for troubleshooting in those applications. The nice thing about doing IV curve testing at commissioning is it gives you a historic record, so you can ensure that the modules were working properly when the system was installed. The nice thing about IV curve testing is you can identify deviations from the IV curve that you would not find just by doing open circuit voltage or short circuit current testing. So it can find problems like notches in the IV curve, reduced slope on either the horizontal or vertical legs, reduced power point. Fluke has 3 IV curve testers in the portfolio. The SMFT 1000 can test up to 1000 volts and 20 amps. The Fluke Solmetric PVA products, actually it's the 1500 T2 and 1500 HE2, are capable of testing up to 1500 volts, 30 amps. The HE model is specifically designed for working with high efficiency modules, so it can test up to the full 30 amps, regardless of what the efficiency of the module is. The 1500 T2 model will test up to 30 amps to 18% efficiency. When you get to 19% or greater, the current rating drops down to 10 amps. Another test done at commissioning is earth bond continuity. This is making sure that all of our metal parts are electrically connected together. Things like module frames, racking, metal conduit, metal junction boxes, combiner boxes, inverters, cabinets, our medium voltage transformer cabinets, battery cabinets. All those things that don't usually carry current need to be electrically bonded together so that if there's ever a fault, that fault has an easy path to ground that's not through the technician working on the system. We're looking for low resistance in this case. So typically looking for 0.5 ohm or less resistance there. The SMFT 1000 can do this earth ground bonding test, and the 1507 insulation meter can do it as well. They both test up to 200 milliamps, which is the requirement of an IEC standard for doing this type of testing. We can also do ground resistance testing at commissioning, and it's somewhat similar to the earth bond grounding measurement, but in this case, we're checking to make sure that the ground rod actually has a really good connection to the physical earth. So again, looking for low resistance there. If the metal parts aren't properly bonded to ground, we can have issues, safety issues. Also, some overcurrent protection devices won't work properly if they don't have a good path to ground. So we've got a couple tools that can do this, the 1630, the 1625-2. One of them is shown here in this picture that is a stakeless meter. The other one has some stakes, so it measures using a supplemental rod that's included with the test device. So again, making sure that the ground rod is actually bonded to the earth well and there's a good solid connection there. Finally, in commissioning, we can do performance testing. So making sure the system is actually producing the amount of power that it should be. We're comparing what we designed it for to what it actually is performing. We can also do inverter efficiency measurements at this point as well. A lot of times we're going to use the data acquisition system included with the system, either the monitoring from the inverter manufacturer or the monitoring that we installed at the system to see how much the power output is compared to what we would expect it to be. We do have some tools that can measure power. The 393 clamp meter can measure DC power. You'd have to calculate the AC power measurement as well. The SMFT 1000 can measure DC power, and then it can measure AC power, and will actually calculate inverter efficiency automatically. It can test up to 60 amps, and the caveat being that you need to be able to get the current clamp that comes with the meter around all of the DC positive conductors. So you got to be able to fit them all in the DC clamp. Now, same thing on the AC side, you need to be able to get that clamp around one of the legs of the AC output. So if you have something like a microinverter where you don't have access to the output conductors of that inverter, it's going to be hard to measure that inverter efficiency in that case. Another thing we do in commissioning and in operations and maintenance is thermal imaging. So we can use our handheld thermography to look at all kinds of electrical equipment, from our disconnects, combiner boxes, inverters, transformers, essentially anything electrical. We can use it also on modules. It's very common when looking at modules to use aerial thermography, a drone with a thermal camera attached to it, although we can use handheld thermography to assess modules as well. The things you need to know when doing thermal imaging on solar: first off, the system has to be operating at a fairly high capacity. Usually you want 600 or 700 watts per meter square or higher, because you need that power flowing through the system to heat things up, so you can see the differential between things that are working and things that are not. Thermal imaging also requires training. You can't just pick up a thermal camera and go out in the field and expect to get high quality data. You really need to get the training that goes along with it to be able to take good photos and get good information. In this photo here, we got a picture of a fuse disconnect. You can see that the fuse on the left-hand side looks a little cooler than the fuse in the middle and the right. That could just be that it's a different fuse, or it could be there's less current flowing through that circuit than there is through the other two, but it warrants a little bit further investigation there. When we have equipment that is hotter than other equipment, it indicates high resistance. We'll get that typically in a connector that has not been torqued down properly. Also, we can look for things that are cooler. In this example here, we've got a piece of electrical equipment. That right-hand circuit there is cooler than the other circuits because there's no circuit actually connected to that terminal. So, of course, that's going to be operating. Well, it's not operating. So it's got a lower temperature than the circuits that are operating. Another example of this would be a combiner box where we've got a series of fuses there. If one fuse is cooler than the other ones, that means that indicates that that circuit's probably not working properly. Doing thermal imaging at commissioning allows us to set a baseline, so we know things were working properly when we installed the system. We can go back to that in the future and see if there's been any changes. You can use aerial thermography. There's many drones in the market with thermal cameras. At Fluke, we have a whole range of thermal cameras, from the small PTI 120 pocket camera that goes for around $1,200 up to the high end, the TI 480 Pro, which is a much higher resolution, and it runs about $12,000 or so. The nice thing about the higher resolution is that you can get further away from the electrical equipment and still get good high quality photos. So you can be outside the electrical hazard zone with the system operating and still be able to get good thermal imagery. The TI 480 also has swappable lenses. So comes with the standard lens. You can also add a telephoto and a wide angle lens as well. A good technique during operations and maintenance is visual inspection. This is actually required by that IEC standard, and we're looking to see if there's any issues with the system. If you are trained and know what you're looking for, you can find all kinds of different issues like burnt out connections, damaged modules. You can find issues with racking. Obviously, something like a missing label would be pretty easy to see. You need to have training to know what to look for to do a good visual inspection, and then it's nice to have some kind of checklist. The SMFT 1000 is a built-in checklist. It's based on the IEC standard. It's a simple pass-fail, and the nice thing about it is you can go through, you can save the results, and then you can very easily export them and put them into a report later without having to hand write things down and transpose them into a different document. Our inverters and transformers are going to need operations and maintenance as well. We can do simple things like AC and DC voltage and current testing. We can check our fuses to make sure that they have not blown. We can do thermal imaging to see slides. We can do thermal imaging to see if there's any hot spots or cold spots. We can also torque our terminals. That's not a tool that Fluke sells, but it's really important to make sure that the terminals are properly torqued. We can also check our inverter efficiency and then do AC power quality measurements, things like measuring our voltage, our frequency, looking for harmonics. We can also look for transient voltage spikes with those higher end power quality meters. Now, I'll just say on this slide here, this is a picture from Europe. This, I believe, is actually the PV array that is installed on our European headquarters in Eindhoven in the Netherlands. That's why you see the single conductors coming out of the bottom of the inverter. That's typically how they do it in Europe. They don't use conduit as much as we do here in the US. We need to do this operations and maintenance on our inverters and our transformers because we want to make sure that the system is working properly. So we need to make sure that we're producing the amount of energy that we're expecting. Also, many manufacturers' warranties require regular maintenance. So we need to do that maintenance to uphold that warranty. If we don't do that maintenance, it will sometimes void the warranty. It's preventing system failure. So a properly maintained system will operate better than others. It will also maximize that production. And we have a whole suite of tools that can be used in this operations and maintenance. Our multimeters, our clamp measures, meters for measuring current. You can use torque tools. We got multifunction testers like the SMFT1000 that combine a bunch of different tests all into one device. Power quality meters, thermal imaging cameras. Basically, we have a tool for every test that's done in solar at this point. Networks, too. We don't talk a lot about networking, but most of these systems have some type of networking equipment. So you'll have that to maintain as well, especially on utility scale systems. And we've got tools for testing networks, both with copper and fiber. Now, harmonic issues can be a problem. Usually it's coming from the utility or from a load in, say, like a manufacturing facility. Very, very rarely do we have problems with the inverters creating power quality issues. Some of these power quality meters can also be used to conduct load studies. And those are really good if we're including behind the meter energy storage to offset loads. We can identify how much energy those loads are consuming and then size our energy storage system appropriately. As I mentioned, some of these power quality meters can also measure transient voltage spikes, so they can see those very fast increases in voltage. We can also do not load studies. We can do monitoring with these for a period of time. Some of them can be left for even up to a month and do data monitoring. So it helps us find intermittent problems with our system. Our modules will also need some operations and maintenance. A really easy test to do is just a visual inspection, walking down the array, looking for problems. Obviously, this picture is a good example of an easy problem. That was an arc fault that has led to an open circuit. We can see that it's burnt out and caused some damage to the backside of that module. We can see a broken glass, damaged cells often you can see visually, problems with the racking, things like that. We can also use thermal imaging to inspect the modules. Aerial thermography is the most common way to use thermal imaging to assess the condition of modules. It's kind of counterintuitive, but a section of a module that is operating will actually be at a cooler temperature than a section of a module or array that is not operating. So hotspots indicate something's not working properly. And that's because the electrons in a section of non-operating array don't have anywhere to go. And so they're just sitting here in this energized state, and they release some of that energy as heat. Makes it very easy to see things with thermal imaging. Here, the picture of a defective cell, we don't have the visual picture there to see what's causing that, but there's something wrong with that cell. And that's both the front and the back side of that module. In our modules, we can also test for current and voltage. Maximum power voltage testing can find shorted bypass diodes, so we're losing a percentage of the module output. Current testing can find strings that aren't working properly. Most commonly, we're going to do current testing looking for absence of current. So we've shut the system down. We want to open up a non-disconnect rated, non-load break rated disconnecting device, something like a fuse holder or like an MC4 connector between modules. If you open those up under load, it's going to damage the terminal. It's going to cause a safety hazard to the technician, and it could, if it's in a combiner box, potentially cause a catastrophic failure with your equipment. So the technician here using a 393 clamp meter, looking for the absence of current. So there's no current in that circuit, so they could go and open up those MC4 connectors without worrying about arcing. So when we're doing our operations and maintenance on our modules, we want to do a visual inspection. Again, the checklist is a great thing to have when doing visual inspections. We can use our thermal imaging, either with a drone and aerial thermography. We can use our handheld thermal cameras. We can check our voltage and current with multimeters, clamp meters. And I should mention here that if we're doing current testing, we're never using the probes of a multimeter to test for current. They're typically limited to 10 amps. But what happens is when you put the positive and negative probe on the circuit, you're short-circuiting that circuit through the meter, which is how it reads the current. When you remove those probes from the terminals, that circuit is still active unless you have a disconnect in the circuit and shut it off. So what's going to happen is it's going to arc across that probe to the terminal. That's going to damage your probe. It might damage the terminal, and it's a safety hazard to the technician doing that test. So if we're doing current testing, we're always using our clamp meter. It's a non-contact current measurement. It can measure up to significantly higher current levels than we could with just a standard multimeter. We want to make sure that whatever meter we're using, it's rated for the proper environment that we're working in, as the proper category rating, and the voltage rating higher than whatever voltage that we're testing at. Now, this photo here is a picture of the backside of a module. We've got some cracking in that back sheet. You can see the line right in the middle here where the cell in between the two cells, you can actually see right through the back sheet and right through the front glass there. So obvious visual inspection, that's obviously damage there. Also, I see a bunch of hanging wires down here. Hanging wires always drive me crazy because those are just going to get damaged over time. So that would be a red flag for me. Let's talk about ground faults. So ground fault is an unintentional connection between a current carrying conductor and a grounded metal part. So this is our positive or negative on the DC side has come into contact with something like the module frame or the racking. So we're losing energy out to the ground. There's two main types of ground faults: a solid ground fault where it's always making contact, and an intermittent ground fault that comes and goes. And there's several different things that could impact an intermittent ground fault. They're most common to show up in wet conditions where there's reduced insulation value, increased connectivity between our conductor and our metal part. Sometimes you can see wires that are pinched by a tracker, so it moves into a certain position in the day, and then you get a ground fault when it hits that certain position. There's lots of causes of ground faults. Wires that are pinched between things like the module frame and the racking during installation, wires that were damaged when they were installed. A very common one, which develops over time and kind of starts as an intermittent ground fault and usually works its way into a solid ground fault, is the insulation is rubbing, or the wires rubbing up against some kind of part, and over time it rubs that insulation away, and now it's making contact to the metal there. Those are challenging to find. So how can we find these ground faults? Voltage testing in a PV circuit can be used, and we'll go through some examples of that. I'm going to measure from the positive to the negative to see what my open circuit voltage is, and then measure from positive to ground and negative to ground. And under normal operating conditions, assuming that there's not a connection to ground in the inverter, measuring positive to ground and negative to ground should come up with 0 volts because there's no potential between those sides and ground. When I'm doing that testing, a lot of times we'll see some voltage show up at first, and then it will slowly trickle down to pretty close to 0. That's just ghost voltage. It'll bleed off really quickly. If it stabilizes at a certain point, then we've got some real voltage there. We can also use insulation resistance testing. It's particularly helpful to find intermittent ground faults. So it's not going to tell us where the ground fault is exactly located, but it's going to tell us at least what string has the ground fault. And we may be testing and we may see insulation resistance that's above what the standard we're using says, but maybe it's lower than what we expect, or it's lower than other things that are similar in the system. That would be a cause for concern and something that's an outlier, and we want to investigate further. So an example, I was doing testing on a roof-mounted commercial system. This was a low slope, essentially a flat commercial roof. Doing insulation resistance testing, every string was exceeding the maximum of my meter, which was 2 giga-ohms, except for one string. And the one string had like 156 mega-ohms or something. According to the standard, that was a passing test. The IEC standard, or I think, calls for 1 mega ohm minimum resistance to be passing. So 156, way above 1 mega ohm, but it's significantly less than what the other strings in the system were testing at. So when I went out into the array, I found the string, and I found a MC4 connector between modules laying on the roof in a puddle. So that's why the insulation resistance test was less. Once I pulled it out of the puddle, hung it up properly, let it dry for a little bit, it passed the test with 2 giga ohms, like everything else in the system. Ground faults can be a safety hazard. You could have energized metal equipment. It could be a fire hazard because that fault could be arcing between the conductor and the metal part. That it could be a ground fault and an arc fault at the same time. Those arcs can actually lead to sparks, which may set things on fire. I've heard of systems that are ground-mounted systems where they have so many ground faults that they were sparking and setting the grass on fire, leading to grass fires. So it also reduces the system production beyond being just a safety hazard. So we have electrons going to ground, they're not going to my load and creating usable energy. So I can use digital multimeters, clamp meters to measure voltage. I can use my insulation resistance testers to look for faults in the insulation as well. So let's look at an example, and I'm going to take a break here and just say, if you've got questions, please put them in the question and answer section. I, as a panelist, don't have access to the chat, so Caitlin can read those at the end, but we're going to get to questions here in probably about 5 or so minutes. Okay, how do I use voltage to test for a ground fault in a string of solar modules? In this example, I got 16 modules. I got my digital multimeter. I have an open circuit voltage of about 53 volts per module. If I test from positive to negative, I get 861 volts approximately. I'm going to write that down. When I test from negative to ground and then to the positive end of the string, I get 645 volts, which is not what I expect. I would have expected 0, so I'm going to write that down as well. And then I'm going to test from the negative to ground, and I get 215 volts. Also not what I expect. I would have expected 0, so I'm going to write that down. So I got this little chart here. If I take the positive to negative reading of 861, divide that by 53, I get about 16 modules, which is the number of modules in my string of modules. So that's what I would expect. Now, my positive to ground measurement was 645. If I divide that by 53, I'll get 12. And then if I do from the negative to ground, 215 divided by 53 gives me 4. And this isn't going to be exact. You'll get decimal places, but it should be pretty close to an even number. So what this tells me is that there are 12 modules between the positive and the ground fault and 4 modules between the negative end and the ground fault. And that means that the ground fault is somewhere between module 4 and 5 from the negative end of this string. So what I'll do with this information now, after I've done these calculations, is go out into the field, figure out where this string is, count 4 modules in from the negative end, and that's where my ground fault should be. And I might have to do some work to figure out exactly where the ground fault is, but at least I know where in the string approximately it's located. Now, another example, and we go through this one a little quicker. Positive to negative, I got the same results as the last one, 16 modules in the string. Positive to ground, I got the same 861, so 16 modules. Negative to ground, I got 0, which is what I expected. What that tells me is there's 16 modules between the positive end and the ground fault, which would mean the ground fault is in the negative home run conductor. This is a relatively common ground fault location in one of the home runs. It's also fairly easy to miss because you're used to seeing 861 and 0. So you may do that positive to ground measurement and see 861 and be like, yeah, that's fine, and then move on. So when you're doing those measurements, make sure to pay really close attention to what measurement you're getting and whether that's the actual expected measurement. Another problem we see with systems in operations and maintenance is arc faults. This is an arcing electrical connection, and there are 2 types of arc faults. Series arc faults are a high resistance connection where there should be a low resistance connection. And this picture on the screen is a good example here. This is a module to module connector where it either didn't get plugged in all the way or somebody made a bad field crimp and there's not a good connection there and it's arcing, and that arcing is causing some heat. Eventually that will continue to heat up and the arc will get longer and longer until it burns out like the connector we saw a couple slides back. Now, the second type of arc fault is a parallel arc fault, and this is low resistance where there should be high resistance. And a good example would be a DC positive to a DC negative or AC line 1 to line 2. This is 2 current carrying conductors that have become connected. So there should be high resistance between those 2 connectors, and there's not anymore. Most of these ground fault or arc faults will continue to arc until they burn themselves out. But between that point, the start and that point, we may have some problems. So one thing we can look for is burn damage. So that's a pretty obvious indicator. We can use a thermal camera to look for high resistance connections. And we're not necessarily looking for a specific temperature, but we're looking for connections that are different than other connections that are similar. So if I'm looking at the back of the modules, looking at my module interconnections, and I see one that's at a higher temperature than the other ones, that's an indication there's an arc fault there. Inverters, all modern inverters have arc fault detection built into them. So they'll throw a fault code if there's an arc fault. What you can do is isolate sections of the array and then restart the inverter and see if the fault goes away, and then you know that the arc fault's in that section. Arc faults can be really challenging to find. There's really no tool available other than the thermal imaging and step-by-step troubleshooting to find arc faults. And I just want to point out this picture. This looks like it may have started as a series arc fault. You can see that gap right here between the positive and the negative connector there. And then I would guess that this heated up and melted to this connector here, and then it became a parallel arc fault. So you kind of have 2 different things going on there, neither of which are good for system performance and safety. So arc faults, big safety risk. They can cause hazards. They're arcing, so there's energy going places we don't want it to go. Series arc faults are eventually going to burn out. Parallel arc faults are going to keep going until the circuit's broken and the current stops. Here in this picture, this was a module interconnection, like a MC4 type connector here. And you can see that the male side here was not inserted all the way into the female side of that connector. So there was a high resistance connection there, and that burnt out the connector and also ended up causing a fire on the roof of this building. So obviously we want to avoid them. So thermal cameras and using a troubleshooting workflow are really the only ways to find arc faults at this point. Now, once I get all this test data, I need to document it. There's no point in recording test data if you're not going to do something with it. We need to record the data in a way that's easy to capture, easy to catalog it, retrieve it, and it has to be accurate. Having consistent workflows will help from that, especially when we have new technicians. This is an example of the report capabilities of the SMFT 1000. So the nice thing about that is I can save the data on the tool, I can export that to my desktop software, and then I can report out on it without having to hand write things down and do a manual collection and analysis. And of course, our test tools need to be calibrated. Most Fluke tools require annual calibration or read whatever the manufacturer's specifications say. Some operations and maintenance contracts will require calibration before you go out to the job, and they're going to want to see an actual certificate of calibration. Fluke has calibration services, so we can provide those as well. So to wrap things up, you've got to have the right test and measurement tool. It has to have the proper category rating for the environment that you're working in, depending on how close to the source of power you're working. And it has to have a voltage rating above whatever voltage that you're going to be working at. You need the right tool for the job. So make sure that you've got the tool that's going to perform the test that you need to conduct. We need to calibrate our tools to ensure that they're accurate and we're getting good measurement. And finally, we didn't really talk about this, but it's extremely important. We need the proper personal protective equipment for the equipment that we're working on. So if we're working on energized equipment, which we're often doing in the solar industry, we need to make sure that we've got the personal protective equipment that's going to keep us safe. Now, in this picture, this technician has all the right equipment. They've got electrically insulated gloves, FR-rated clothing. They've got their arc flash face shield, the balaclava, and yes, he is kneeling on the ground. That's not necessarily a best practice because his knee is making a lower resistance path to ground than the sole of his rubber shoes are. So it would be better to be crouching there instead of kneeling. But he's got all the right equipment on, which is really the key in this case. So we've got some time for questions. Again, put them in the question and answer section. If you need more information, you can also go to Test Equipment Depot. They have this website specifically for Fluke tools, where you can go and get information on those tools. You can purchase them right from the website, and you can also get quotes if you're buying more than a couple tools as well. So, Caitlin, do we have any questions in the chat that I can't see?
I don't see any questions at the moment, but if you do have any questions, please drop them in now. But thank you so much, Will. This has been wonderful.
Yeah, no problem. And if you have questions in the future, feel free to reach out to Test Equipment Depot. They'll be available to answer your questions. If they're more detailed questions than they have knowledge of, they can reach out to Fluke, and I'm happy to answer questions as well.
Thank you so much. And thank you all for attending this event. Again, all of the products that were featured here today for Fluke are available, and we do have a lot of them in stock and ready to go if you're ready to make a purchase. Or if you need just more information, how much does something cost, our sales team can get you a quote. And if you have just questions in general, we can definitely get you in touch with either Will, or we can find out and relay the information back to you as well. That's all I have for today. Let me just double check that there's no questions in the chat, because I don't want to leave anybody hanging if you are. Okay, so that looks like it's going to do it for us today.
Well, thanks for joining, everybody. I hope you learned something and have a great day. And we'll see you at all the solar trade shows if you're attending. So stop by the Fluke booth.
Thanks so much. Thanks, Will.